Welcome to the class Artificial Neural Networks. This is part 3 of the first lecture on deep networks. In this part, I would like to introduce the notation for multilayer networks and take the first steps towards a derivation of the backprop algorithm. The backprop algorithm is the most famous algorithm and is at the heart of today's lecture. We have already seen that we can use a single network with one hidden layer to solve something like the XOR problem. Now, the XOR problem was solved in the previous part by an explicit construction. The question is there a way to automatically find the correct weights, find the correct location of the hyperplanes so as to solve a problem like this one and even much more complicated problems? In the end, we will be interested in a network which takes complicated inputs, such as these images, and it gives an output. And we use a classifier in the form of a multi-layer network, not just with one hidden layer, but maybe with 25 hidden layers, maybe with 100 neurons in each hidden layer. And we will compare the output of the network with the target output that comes from our database. And this comparison allows us to define an error measure. Let's look here at the example of this two-layer network. We apply an input pattern x mu in layer 0. There's an intermediate layer 1. And then this is the output layer. The output layer has 2 neurons. And this is the output for pattern mu. So the output for pattern mu is the neuronal output of these neurons in layer 2. And this is the upper index here is always the layer index. The lower index is the neuron index. Now this neuron I in layer 2 has an output which is a nonlinear transform of its activation, of its total drive. And the relation could be this sigmoidal function or some other functional relation. What can we say about this activation? Well, the activation of this neuron here in layer 2 is caused by the inputs from neurons in layer 1. So the outputs of neuron in layer 1 are the inputs for neurons in layer 2. So this drive, this activation, is the sum over all the neurons in the previous layer. So I denote the weights to the second layer with the upper index 2. That's a convention. One could do it differently. That's my convention. Now, the neuron in layer 1, neuron J in layer 1, has a certain output, which is again a nonlinear transform of its activation, which is again a sum over its inputs, and these are then the actual inputs. This is layer 0, where we apply pattern mu. So here's a network now with 3 layers. This is layer 1, this is layer 2, this is layer 3. And let's look at this specific way, this specific weight. This is the specific weight in layer 1 leading to layer 1. And it connects the second neuron in layer 1 with the third input in the input layer, in layer 0. Now, we would like to change this weight such as to minimize this error. So we minimize the error by gradient descent. We go down the error surface. The error is the sum over all output neurons and the sum over all patterns that we have in our database. So this is the error function. We want to take the derivative. We have to plug in here the value of the output. This is this value here. This depends on the activity in the previous layer, in layer 2. The previous layer depends on the activity in the first layer. The first layer depends on the input in layer 0. So we just have to take the derivative, and to do that we apply the chain rule. What I suggest is that you pause the video now for a few minutes, take 5 minutes or 10 minutes, whatever you want, and apply the chain rule. And this should give the update. Okay, I hope you have tried to calculate the gradient of this error function with respect to this specific weight. Well, if you got stuck the first time, it's not a problem because the chain rule gives many terms. So this is a complicated function. Let's look at this function y. The output is just a transform of this total activation of this neuron I in the third layer. But this activation is just the sum over the inputs in the previous layer. These inputs in the previous layer are, again, nonlinear transforms of their activations. And these activations can be written by the inputs coming from layer 1. And these inputs are, of course, the outputs of those neurons in layer 1, which are driven by their activations. And the activations are the drives that come over all the weights from layer 0. And this is really the input into the network. This is where we apply the pattern. So the pattern is, the input is connected to the output by this rather complicated function that has many compositions, many insertions. And if you apply the chain rule, you have to apply chain rule many times in a sequence. So to help you with the chain rule, the first step is to identify intermediate variables. So I already underlined these red activations. These are the drives of the neurons. And then we also have the activations of the neurons themselves, the neuron output, not the activation, but the output of the neuron, the activity of the neuron. The output of the neuron 2 is the input of the drive for neuron 3. And the third variable is a specific derivative. In the end, we want to take the derivative of this error function with respect to one specific weight. And we take the derivative with respect to one of these intermediate variables, one of these drive variables or activation variables. And these deltas play an important role in the backpropagation algorithm. So step 1 is we identify these intermediate variables. Step 2, we write the weight update with these new variables. So let's try to do this. So we are interested in the change of a weight in layer 1, the weight from the third input neuron to the second neuron in layer 1, and this is just a gradient. And now we use the chain rule and say, okay, but this weight depends on this weight is coupled with the activation variables of the same layer, and so this is just a chain rule. And now we can identify this term here is exactly our definition of this delta. And well, this term we have to calculate the activity of a neuron K in layer 1 depends on the input. I take the derivative with respect to the weight 2, 3. So out of this sum, 2L, only one term remains, and that's the term L equals 3. And so this is X3 in layer 0. So this is now our update rule. Now I derived this for the change of the weight 2, 3 of layer 1, but analogously we can write the formula for all other weights in all other layers. So from step 2 we have this nice summary that the weight depends on a product of delta and x. So let's look at this specific weight This is a weight in layer 1. This is the weight which connects the input neuron 3 with neuron number 2 in layer 1. So suppose we change this weight a little bit. Gradient descent is about changing weights. Let's suppose we change this a little bit. Then as a result, this neuron will also change a little bit. And then this neuron will also change a little bit. And these changes will finally give the change in the output. And that's what we want. We want to reduce the error. So let's look back at this graph. So we have set here the delta that goes into this product can be calculated like this. Now this is sort of a little bit of a cheat because we still don't know how to calculate this. And so we have to apply the chain rule again. And so we can say the change of the weight here depends on the change in the activation variable here, but this activation variable will influence activations variable there. And so we have to sum over the activation variables in one layer further up, here in layer 2, and evaluate this individually. So let's look at this term. A2 is this, but the output of layer 1 is in turn given by its activation. So if I take the derivative, AJ2 with respect to A21, so A21 it means that only k equal 2 survives. So this term here gives just Wj2 times G prime. And this term here is just the derivative, it's just the definition of the deltas. So now this means the delta in layer 1 depends on the delta in layer 2. The delta in layer 1 depends on delta in layer 2. The delta in layer 2 will depend on the delta in layer 3, on the delta in the output layer. And so if we evaluate gradients, then we have to first calculate the delta in the output, and then we get the delta in layer 2, then we get the delta in layer 1, and then we can update finally this weight. But with the same kind of formula, once we have the deltas and the x, we can also update all other weights. Let me summarize. So to calculate the gradient, we apply the chain rule. In step 1, we identify intermediate variables, the activation variable or drive variable, which depends on the output of the neurons or the activation of the activity of the neuron in the previous layer. And then we have these delta variables. We can write the weight update as a product of the delta variable with the input. So in layer 1, 2, 3 is this weight here. And what we use is the x of this layer and the delta of this layer. And then the deltas themselves in layer n-1 depend on the delta in layer n. And this is why we first have to calculate the deltas here and then the deltas over there. So these deltas, the calculation of the deltas have to be started at the output, and then the information goes backward through the network, and this is where the term backpropagation comes from. So calculating the gradient in the multi-layer network, well, you just write down the chain rule. But since the chain rule has so many terms, it's important to keep things clear. We need to analyze the dependency graph. We have to store intermediate results. We update the intermediate results while proceeding through the graph. And this is exactly the principles that are known as dynamic programming. And once we have updated all the deltas, then we can update all the weights. All the many weights in the network are updated together at the end once we have calculated the deltas.